Hello everyone. I hope you could hear me. Could you please confirm that you are able to hear me properly? Maybe give a little thumbs up. That would be better. Hello. Hello. Could you please confirm somebody that you could hear me? Okay, perfect.
Yes.
Yeah. Thanks, Sushant, for confirming. Perfect. So first of all, thanks a lot to all of you for joining this session. So today we would be joined by uh, Adityavir Raswan. So he has been working in this domain of autonomous driving for past 8 years. He has like huge experience from his previous teams at Waymo and Wabi. And apart from that, he also holds master's degree from Clemson University. It is one of the prestigious university in USA. So he would be joining us today, and he would be delivering talk on motion prediction and motion planning. And just to give you like a little bit more context, these are the two important things whenever we are like thinking about building autonomous driving stack. So that's gonna be all about this guest lecture. But apart from that, to give you a little bit more info about who I am. So my name is Mayur. I'm a founder of Cloudby Robotics, and we are working in physical AI. So that's nothing but like AI models integrated with real robots or humanoids. So we are building web application where we would be helping customers with synthetic data generation, training neurosymbolic foundational models for robotics, and eventually providing evolutionary layer for this robotic AI models. So this is something we are providing at Cloudby Robotics, and this is like our main core business. But apart from that, since I've been working in this domain for like around 6 years, so I've been also doing this thing for like various other topic inside autonomous driving. So this is like a new bootcamp that we are releasing, which is something Aditya would talk about in more details. But apart from that, we also conduct other bootcamps that something would help you to learn skills about autonomous driving. So the first bootcamp that we deliver, that's about AI. So inside AI bootcamp, we cover all the things that are necessary to build your perception stack. So you would learn about machine learning, you would learn about deep learning, computer vision, and you would also learn about vision language models or VQA, or in the end, you would also learn about data generation using diffusion models. So that would be our first boot camp that we would be conducting. That's something already running at the moment. Apart from that, we conduct second bootcamp that's about uh, controls. So as you all know, when we are like talking about build controlling autonomous car, so in that situation we need to know about vehicle dynamics, but that's not all. We also need to know about various control algorithms. And so the second bootcamp that we are conducting would be covering like these three areas. We would be delving into vehicle dynamics for like longitudinal lateral direction, and then we would be looking into controls, linear control, optimal control, and also stochastic control. And in the process we would build like three projects. That's something you could put out on your profile. Apart from that, we conduct our third bootcamp. Perfect. That's about ADAS, and in ADAS bootcamp we would be building like ADAS project. We would be building automated emergency braking system and adaptive cruise control, and we will be doing this thing with the help of model-based design methodology or V diagram. But I would be walking through end-to-end process from like getting requirement from stakeholders and converting eventually that into like proper design and performing verification and validation. So that's like third, and in this process there is like missing link, and that's motion prediction and motion planning. And this is something already included in our ADAS bootcamp as a lecture, but like more emphasis should be given on this one topic. That's the reason I got in touch, means Aditya and I've been like connected for a while, and then Aditya suggested that we could do something together. And since he has like such huge or like really good expertise in this domain, he would be first walking us through this particular domain in the beginning. Yeah, this meeting is being recorded, so don't worry about that. And so he would be walking us through motion prediction and motion planning in this guest lecture. But if you are interested in learning more about this domain, if you would want to build projects, then I would recommend joining our boot camps. That's something would start late December or in first week of January. And that in that boot camp, we would be building like three projects. That's something that they would tell you in like more details. But yeah, just to give you like a little bit teaser, we decided we could have like a guest lecture, and I guess Aditya has joined this call. Welcome, Aditya, to this call, and thanks a lot for getting early. I know it's like quite
Yeah,
early in USA. Yeah, thanks to you for that.
yeah. Thank you, Mayur. Yeah. Sorry, guys, I'm a little late, but yes, it's early for me, but I'm all ready. And thank you so much, Mayur, for hosting these talks as well as the all the presentations and as well as the boot camps that you have. It's very inspiring, and I just wanted to contribute to it in my capacity with my experiences. So that is where, like, yeah, I wanted to get this started with. Uh, so we can get started with the this introductory guest lecture. The idea is here just to give you a high level overview of different things. Mayur, can you share the presentation?
Okay, I'll make you co-host so that you would be able to share your
Yes,
screen
thank
as
you.
well.
Yeah,
Yeah.
and before like we get started, I just wanted to we are recording this, right, already?
Yes, yes, we are recording
Nice.
it.
Yeah. Yeah, before we get started, I just wanted to maybe get a little bit of an idea of where everyone is currently, like what journey are they on, just to get an idea of like what sort of people we have here. So maybe like a few people, if you can say a little bit, that would be nice.
Yeah, I have made you co-host, so you could check whether you could share your screen and
Yeah.
maybe presentation as well.
Yes. 1 second.
Can you?
Yeah, yeah, I can.
Yes, we could see it as well. Okay, perfect.
Yeah. Yeah, so maybe Mayur, you probably know a lot more. You can let me know. So, are most of the people here from they are students or they are already professionals early in their
Uh,
career?
yeah, Aditya, over here it's quite a mix, and we are having people from Europe, we are having people from USA or like North
Mhm.
America, and also we are having some people from Vietnam and Japan as well. So it's quite a mix. I know who all have joined this call, but we do have like students, bootcamp from these nations. So it's quite a mix. And in terms of experience, we do have like people who are early in their career. Some of them are like doing masters, or some of them are working either here in India or like abroad. But yeah, it's quite a mix. We are also having some PhD student in these boot camps. So all of them are like eager to hear from you and learn more
Mhm.
on the journey.
Yeah, sure. Yeah, so I would just say that before we get started, like I want this to be more interactive rather than just me like shouting out what I know. It would be nice if you have questions, stop me then and there. We can have a small discussion if the time permits, and towards the end we will have a Q&A as well. So if you have questions you want to ask in the end, that also works. But yeah, feel free to stop me in the middle. Yeah. So a little bit about me. Yeah, I have been professionally in the autonomous driving space now for 6+ years in US, and out of those 6 years, I was at Waymo for most of it. This was after my master's in automotive engineering. But all of this, yeah, the master's was also focused on autonomous driving, which was very new at that time, back in 2017 to 2019. That was the, for me, the cool thing to work on. So yeah, I was a part of that master's at Clemson, focusing on that.
Recording in progress.
Oh, There's some echo grinding.
I think
Yes.
someone is not muted.
Okay, I think it's all good now. Yeah, so after so being in Waymo and then after that Bobby, which is a smaller startup in the space, which is focusing on slightly different vertical in autonomous trucking compared to robotaxis. So I think like now I have a broader set of experience in the industry. Uh, it's still a very fun industry to work in. There's a lot of unsolved problems still where like we have a lot of deployment already started, but there's still a lot of scale to happen. And the challenges are always enormous because the bar is really, really high for meeting superhuman levels of safety and also like getting through these challenging environments. So I just wanted to like get started with first, what is the prediction and planning module, right? So Mayur has already told you many things about the whole autonomous driving space. So I don't want to go into a lot of details there, but just to give you a high level idea of why the prediction and planning matters is essentially the purpose of prediction and planning is to do everything that our brain does. So that's what we are trying to do here. We are trying to perceive the environment. That's the perception part. But beyond that, predict where those all of the objects and all of the classified agents in the scene will be in the near future that we care about. So that is where humans do this very intuitively. We have a massively enormously evolved brain. It can do reasoning about these things, complex reasoning, but we are trying to capture these reasonings within machines. So yeah, predicting what the other agents in the environment, how it will unfold over the next few seconds, and then what should we do in that environment which unfolds, which is safe and also takes us to our own destination or whatever our objective could be. So I just wanted to start with a high level industrial overview of what is going on currently. Yeah, there is some really cool scaling going on. I would say this map shows how exactly it is going on. Do I have a pointer here? Okay. Uh, okay, maybe the mouse pointer works. Hmm. Yeah, so the scaling that is going on is very interesting, as in there is a hotspot here in US, mostly led by Waymo, and now we are starting some other players joining in, but then there's another hotbed in China where there's so many players and they are also scaling rapidly. So it I think this mirrors the market that we have for LLMs as well. This is perfectly mirrored in both of these things, I would say. And within US, that's where I have more experience in. Yeah, as I said, Waymo is already in 5+ cities and they're planning on, I think, 4 more cities by next year. So, and even going international, which is really nice. And then in China, the cities itself are already very large. But I would say, in terms of scale itself, Waymo and let's say Baidu, Polo, Go, they are kind of doing similar trips if you trust the sources on this. So which is really interesting that there is two of these competing giants, but then there are other players within China who are also scaling. And I also wanted to like touch on autonomous trucking. For autonomous trucking, Aurora is currently the only one that I know in US that actually is fully driverless on highway, and they are doing some small scale deployments across different of their domains, mostly in Texas. So most of the trucking industry is centered around Texas in US because of the all of the regulatory approvals that Texas is able to provide to them. And there's a massive hub in Texas for for the freight industry. So that is there. And then Kodiak itself, which was in autonomous trucking, they pivoted to off-road driving, and they have some pilots doing some off-road deliveries for trucks, for giant Class 8 trucks. These are massive trucks on these roads. So yeah, and then we have some early deployment from other players like Zoox, Tesla that we have here, slowly starting to add some supervised drivers in their car, and then yeah, some other players which sadly are no longer here because of any kind of industry that goes through this has this consolidation phase where a lot of investment is poured, and sadly not everyone will survive. So that was the fate for Cruise, Argo AI, TuSimple, Embark, Uber ATG for different reasons, all of them. So I just wanted to touch upon like, okay, it's not all been smooth sailings. We know what happened with Cruise, we know what happened with Uber ATG. So those are some of the key lessons for the industry we should all be looking into. And I just wanted to start with that itself. So the two things that we see here are like the two endpoints of like how I saw this while I was in the industry. The first one was, we all know the Uber incident that happened. I will not show the whole clip, but we all know what happened there. So the systems were designed to be safe. It had the lidars, but the policy making on getting these technologies out on road were the ones which were the culprit and not the technology. So yeah, there were some corners that were like shut down and cut because of this. We had such issues, and someone unfortunately lost their life in that. And then like over a longer period of time since then, Waymo has shown how safety can be achieved, and they have shown it like on lot of miles, millions and millions of miles of driverless cars, and having a perfect safety record, like, which is really nice to see. And now there's a point where statistically they have enough data to compare it to some human data. So they have done some of these comparisons in with different industries, with some insurance companies. I think there was Swiss Insurance, and then recently with TUV SUD, they have some more third-party validation going on. And more than that, it's just we all can hail that car, we can use that car. And I've worked on it, so I know a lot more of what goes into it. And I know that it's still far from perfect. Uh, and we will get to more of those things as well. But yeah, having industrial regulation is good. Like in US, we have NHTSA and also the DMV, which also give out the licenses, and also they ensure that any kind of operation, they are actively reporting all of their operational performance reports, as well as their numbers that are critical with these agencies. And there's a back and forth, and your license can be taken away from you, which in case of Cruise we saw that happened, which yeah had other knock-on effects. Yeah, any questions from anyone at this point, just a high level, or we can get now yeah.
I have like a very simple question. So I see that there is a lot of, I think I can echo, I can see the hear the echo of my voice. I don't know. Okay, so my question was that so if we see most of the times, like in US, we see a lot of potential and a lot of like markets where autonomous robots, autonomous vehicles are used. Like even a lot of autonomous vehicles that are not in Germany, but they are in US. It's the same for delivery robots. Uh, I know your more expertise are more towards the US market, but what are your insights on why is it that these robots are not in Germany or in Europe mostly, but they are mostly seen in there? Yeah, thank
Yeah, yeah, yeah. Thank you, Junaid. That's a very nice question, and I think that is more to do with the landscape of how these countries view technology and regulation. So it's not that Europe cannot have these robots technology-wise. They definitely can. Scale-wise, they definitely can. Financially as well. It's just the kind of investment that you see in US or China for these things surpasses what we see in Europe. I think first of all, investment. Secondly, the regulatory environment in US is more supportive for most of these ventures. There is US itself is also broken up into different states, and each state funnily has its own laws. So as I said, in the case of trucking, you'd be surprised. California, which is like the bedrock of robo taxis, or in general, like all the Silicon Valley, everything, trucking is kind of almost banned. Autonomous trucking currently. There's legislation going on to get that into motion so that we can have autonomous trucking here. But on the other hand, Texas itself has regulation which is more conducive to other such ventures, such as autonomous trucking. So I think this is more of a problem that we see on the authority and the regulation side, which I think is a strategy which European Union has in general for regulation of technology. And yeah, it's there's nothing more to it in my opinion. Okay.
Thank you.
So, yeah.
Can I ask a question? Am I audible?
Yes, Raghu, go ahead.
Yes, this is a question about Waymo. I recently read an article. I think it came on Wired.com or something like that. I forget the link. I'll try to bring up the link. Basically, what it said was Waymo is not actually fully autonomous. There are like people, have controls behind the scene. For every vehicle,
Yeah.
there are like two engineers who are like monitoring it and things like that. So and this is, I think, true for the other robo taxi
Yeah.
startups as well. So can you shed some light on it, because this is not very widely known, I think, or yeah, maybe your industry insights. Thank you.
Yeah, definitely. I will share whatever is already public. Like Waymo itself and other players have spoken a lot about it, and I echo all of these things to be what I know to be correct. Um, of course, when you're making something which is fully autonomous, it is not, the technology is such that currently it cannot do everything. Otherwise, we would have self-driving cars everywhere, right? So currently, most of these are geo-fenced within a ODD that we have. And that is, of course, it is also, there's a regulation part to it, but also you want to control and know where your technology works and slowly expand it. So both of these things are there. And then I would say that after that, like what you're talking about is, in case of Waymo, is called remote assistance. So there is no direct control. It is a remote assistance, and the way these assistants work is very much like a call center. So what happens is, when Waymo sees something which it does not understand, let's say there is something in front of it which it doesn't know how to interact with, so it will come to a stop, and it will almost call this call center and ask these people who are looking at their screens. They have all the information from all the sensors, and they can tell the robot, the vehicle in this case, that hey, what you're seeing right now is something you can ignore or you can pass around it. So this is more like a calling a friend for help. And the only thing these remote assistant people do is maybe guide the car as to where it should go. At no point are they indirectly in control of any of the controls of the car, because it is a very risky, and they don't want that kind of risk in their system. So the car is making the decisions, but it is being guided by an remote operator. So that is like an important distinction that I've seen in the industry. I can't say that is true for every player in the industry, but I would believe that for most of them, that is the model. And again, like the ratio that you're talking about of two engineers versus one engineer, or like one car, I don't think that is correct. Even when I was at Waymo, that was not correct. It was, they have flipped that ratio around to be financially productive. So and you can think of it like, at any point of time, the car is not calling for help. right? So it's the utilization of that agent, the assistant, is
Mhm.
not that high. So maybe you can get away with having one person per 10 cars, and the idea is to have eventually one person 1,000 cars, so that
Oh,
financially this makes sense.
okay, okay. Because the article I read, it seemed to suggest there were like two or three people for the whole duration. They were, engaged. Okay, so maybe
Yeah,
I'll try.
share that article with me. I
Yeah,
am
yeah. I'll try to bring up that article, and it was from on a major publication like Wired.com or something like that. So I'll try to bring it up.
yeah, because this is something which is a very public information from these companies. Now, like, of course, you have to trust a little bit of what the companies are saying, but I've been inside and I know that, like,
Okay.
that is how it is.
Wow, but it's very nice to hear that one person can, be in control of like 10 cars, it's like switched.
Yeah,
Oh, okay, thanks.
yeah.
Can I share something? This is Muralidharan. I'm a research scholar at NIT Calicut, Kerala. Recently, I've been to Dubai for attending self-driving Congress. It was held at on September 24th and 25th. Um, it's a nice experience. I had a view of all the autonomous taxis and air taxis, autonomous air taxis also they have in the display. Even I had a chance to travel in the Apollo autonomous robo taxi, but I could not because I depend on public transport. They asked me to travel to somewhere else to get into the taxi, so I could not make it. But it was a real experience, nice Congress. I attended that. Even I have a video of those inside how the robot taxi looks like. If you want, I'll share in the group so every one of you can get into the feel of that robot taxi and all. Yeah, and also I have one question. See, you said some people are controlling because it could not identify which object. Suppose sometimes, not all the times. So in that case, can we write AML deep learning computer vision algorithm to detect multiple objects and train it and put it in the ECU? In that case, how much capacity or computing capacity of the ECU is needed?
Mhm. Yeah, Murli. Definitely, like what you're saying is already being done. We
Mhm.
have different sensors, different modalities of sensors.
Yeah,
So, like a camera, LiDAR, and radar, they
right.
are efficient in different domains. And the
Mhm.
way the sensor fusion works is it will take all the sensor data from different modalities, and it will build up a coherent model of the world around it. And all of these
Okay.
modalities only help to improve the certainty of where everyone is. But
Mhm.
again, there is no point at which you are 100% certain about any object. It is all a
Mhm.
probabilistic world point of view
Okay.
that you have. So
Okay.
there is already, like, all of these autonomy vehicles have these sensing and prediction and detection and prediction capabilities in them.
Mhm.
It's just that they
Okay.
are coming up with so many edge cases that they are have to they have to improve on those things.
Mhm.
And any kind of issues that you're seeing are more
Yeah, even there are some layers of autonomous, right? Level one,
yeah.
2, 3, and 4. But 4 or 5 is not yet, it's a fully autonomous. It's not yet achieved, right?
It
The
is
full,
level 4 is achieved in multiple
okay. Level
places.
5 is not
So
yet.
so what I was showing here is, like, all of the
Mhm.
scaling companies, they are
Uh-huh.
doing level 4 because they are fully driverless in a particular
Okay.
domain, which
Mhm.
is it's not the whole world yet. That's why it's not
Mhm.
level 5. But
Yeah.
within that domain, within those specified conditions, they
Mhm.
do not have a driver inside. So henceforth, they
Okay.
are level 4 already. So this is
Okay.
already, like, and it's surprising for me to like think about it that people don't know this, but Waymo was level 4 in 2019 in Phoenix.
Mhm.
So it's been 6 years when Waymo became since it became level 4 in one city. In my
Mhm.
in my view, it's probably 2019. So yeah, it's
Okay.
been a long time, and now it is more about how you scale this technology, which you have shown is not a research project anymore. Now it's about
Mhm.
scaling it,
Okay.
making sure it's very, very safe, and also it's
Mhm.
about financially, does it make sense? Because you can have a
Okay.
really good technology, but it is expensive to operate. In that
Mhm.
case, you would not be operating that
Okay.
technology, because that's how the finances work.
Mhm. Okay. One more information in Abu Dhabi, they have delivered self-driving delivery cars, robots like to deliver goods,
Mhm.
not a passenger car. Okay.
Yeah, yeah, yeah. I think it's all very new. It's coming up. We will see
Mhm.
more in the next few years internationally as
Okay.
well. Waymo has
Mhm.
announced London and Japan, Tokyo. So, and
Uh-huh.
other companies as well, Chinese companies, they have started.
Yeah. In
I
India
think
also. Mhm.
Zoox had announced something in Dubai. In India,
Mhm.
I'm not 100% sure, but
Yeah, I work in Bangalore. In Bangalore, Wipro and TCS and sorry, IIT Bangalore, IASC have been collaborated. They did research for 6 years and they have come up with a autonomous self-driving
Mhm.
car, but not into commercial. They
Yeah,
have tested that first time
yeah, yeah, yeah.
after
Thank
six
you.
years of research. Yeah.
Yeah, thank you,
Okay, let's
Murli.
proceed. It's taking time. Yeah.
Yes. Yeah, so now, like, we have the high level overview of things. We can get more into the technology bits of, like, okay, what are the current paradigms of how these things work? And currently there are two interesting paradigms, which some companies are going for one or the other. There is an end-to-end paradigm, which is on your left here. It is the most simple to understand, that, oh, okay, you have inputs as your camera sensor inputs, and you have a large neural network, multiple layers, and then the output is the driving steering wheel or throttle, and those things. So this is one capability, or one side of this paradigm. The other would be, in this case, the more classical approach, which is you have different systems and modules, and they are interacting with each other mostly sequentially. So you have a perception module, a prediction module, and a planning module, which goes into a control module. So there is like a proper interaction, and there's a proper definition of the interface between these two things, and the roles are very well divided. It's more interpretable. It's more easy to debug, and I think from a regulation point of view, this system is making more sense currently. But overall, we are seeing these two evolve, and eventually we'll probably have some kind of hybrid in the middle. So I just wanted to discuss that. So coming to the classical stack, how it used to be, how it is currently. So we've always had this kind of different tracks or layers. So in this case, the first would be the perception module, which takes in all the sensor information from the world around you. As I said, different modalities of sensors, camera, lidars, and radars, each having different pluses and minuses. That's why you fuse them together in sensor fusion. And the output of the sensor fusion is mostly object detections. Think about like bounding boxes, and then also classification. Because you have cameras are really good at semantic understanding and classification. So you ideally want to use all your sensors to get a better idea of the world around you. So the perception part is mostly has been neural network driven. Most of them use a lot of neural networks on training data to come up with bounding boxes, as well as like other things. Then there has been like a class called tracking, which is essentially you have your raw data from the perception, the sensor fusion data. You track that using some sort of state estimation, like a Kalman filter, extended Kalman filter, and because that will help you to smooth out the data, and because the data can be noisy, sensors can be noisy. I would say that this over time has morphed into a single module. Perception and tracking has become a single module. And the third module is the prediction module, which is where this is where you're using a neural network in most cases to predict where the agent will be in the next 3 to 8 second horizon, 10 seconds, depending upon your use case. So all of these things, in my opinion, the industry is headed currently towards merging these three blocks into one. So perception and prediction become a single neural network module. So what I'm trying to show here is that when you have multiple of these blocks, any kind of errors that you have for one system, they propagate through and they multiply. So this is just a very crude example of it, of like how, let's say there's a 98% accuracy in perception and then 97% in tracking and 90% accuracy in prediction. So by the end of just these three layers, your accuracy has dropped dramatically. So a lot of now effort is to like, okay, we don't need three different boxes or three different modules. We'll have just a single module doing the perception and prediction. So that those things are being done. Then sensor fusion itself used to be, we got individual sensors, and then we used to like have the tracking or the smoothing run on the individual sensors and then fuse them together. But now we are like, it's a early fusion systems that we are seeing overall coming up, which are able to take the raw data from all the sensors and in one shot generate the tracking, sorry, the detections, the classifications, and the predictions. So that is like one side of the stack. The one that I have a lot more experience is in planning stack. So planning itself is like the interface between prediction and control. So planning will also be, in most cases, the classical planning problem is also further divided into hierarchical planning algorithms. So you have more like a route calculation or like a high-level mission planner at first. Then you have some sort of behavior planning layer or motion planning layer after that. And then you have some optimization, and then it goes, the output of that is smooth enough so that the controller can drive it. The controller itself will convert those waypoints, as to say, and the speeds and the accelerations into the steering and the throttle commands. So we have the control itself has different ways of control, and Mayur has really good I think lectures and boot camps on this, all of these parts. So yeah, the high level overview that I want to like, this is really it's a verifiable system in which responsibilities are defined, and it works really well. You understand each of the interaction. There is a proper like you have your but the problem comes when end-to-end system performance, you have to pick who is the culprit, and then it's hard, it becomes hard sometimes, and also these errors propagate. As I said, like in this example, like just having these accuracies means that by the end, even though none of the single systems was below 90% of accuracy, the overall accuracy ended up becoming 81% in this case. So I think that is kind of the one of the drawbacks here. Another one that I will talk deeper about is the prediction and planning. Here are sequential and not coupled. So I think that is a big issue that the industry is trying to solve currently. We'll get deeper into it. And yeah, and the other side of the paradigm that we talked about is an end-to-end system. The end-to-end system in this case does the exact same thing by taking in the raw sensor input, but replace all of these modules by a large, in most cases, a single neural network. There are some cases where people or companies are using like different neural networks for different parts, But just an example, this is something similar to what like maybe Tesla has, or something like a Wave has. Where we have like different layers, but it is still a single network, which has different parts of different ML components, such as like a HydroNet might have some vision features. Then it will have some layers of occupancy, which can be considered like a occupancy network. And then you can have some prediction module, but those are not explicitly there. It is just like implicitly you are classifying certain layers with certain tasks to interpret them better, maybe to train them better. And the neural planner can be a different class. So I think like that is where the kind of industry is kind of maybe headed into having some blocks within the end-to-end networks as well. That is an interesting area of research. So there are some obvious benefits that you are not having to design a complex system. Like every hand engineered feature does not exist. You're learning from data. And in cases of companies like Tesla, which have a lot of data, I think that makes a lot of sense. But the problem comes in how do you ensure that such a system is foolproof and it can work throughout in different conditions? And how do you explain the decision making out of such a black box? So there are still some unsolved questions. And I think like, yeah, we'll get deeper into those details, but just a high level overview of kind of the exact challenges they exist in this K thing. You also need a lot of GPU, strong GPU on your car, on your self-driving car, for running such larger models. And over time, you're seeing models become larger and larger, especially now the transformer architecture. You're seeing these large modules, like which can be considered similar to like an LLM. So you have your own trained transformers. Now the problem becomes, how do you get these larger transformers, which could be some billions or maybe trillions of parameters, to fit on something which can run in real time on a real vehicle? So that's where things like distillation of these can come into account. We'll get a little bit more into detail, but I think like maybe in the boot camp there'll be more details about these things in general. Yeah, and I would like to like end this slide with saying that these two approaches, there is also like we're seeing convergence of a middle ground, where there is some hybrid architectures where yes, we are relying on these prediction modules and other things, but yes, we are trying to combine prediction and planning in a unified single backbone model. So this is like a transformer itself. So a lot of these companies are working on these technologies where they're trying to solve the joint planning and prediction problem by training a single backbone and having a prediction head and a planning head. So I think this is where the industry is headed in currently. The current area where it is still, I think in production, it's still hard to achieve this, but it is definitely the direction of travel for the industry that we are heading into. Yeah, any questions till this point before we move to the next part?
Based on the first approach, which is the modular planning, where does
Yeah.
the time parameterization of the waypoints happen? On which layer?
For the planning, the time parameterization, there is a time parameterization of the other agents in the prediction. So each of the predictions is not just a spatial prediction, it's a spatio-temporal prediction. So you have a time profiling in the prediction module, and the planning itself is also generating these trajectories, which have these waypoints, which is not just spatial, it's spatio-temporal. They have the time information, and not just that, it has accelerations, it has jerks, it has yaw rates. So other things which we care about for our, let's say, just in general, the smoothness of the drive, the comfort, and other things. which are important for control also to follow. So I hope that answers your questions. Is there anything else? Okay. Sure. Yeah. Anyone else before I move on to the next part? Sure. Yeah.
Sorry, we really don't have any like questions at the moment in chat as well, so we could continue, but just some notification. Murli has shared like video, so if you want to look at that thing, you could like check that, or maybe download it so that you could check that later on. Apart
Yeah.
from that, yeah, Aditya, if you do want to take like break, then we could stop like after 5 or 10 minutes if you wish to.
Yeah, I think we can get with the next module, the prediction module, and then we can take a small break after that.
Sure, no worries. Yeah,
Yeah.
we can continue.
Yeah.
Thank you.
Yes. Yeah, I will get back to the videos and the chat later on as well after the end, if that works. Yes. So 1 second. Did I get out of the? No. Yeah. So coming back here, we now see like, okay, what are the important modules that we have? And prediction is the first one that we care about here in this system. So what is prediction? We are trying to perceive it's trying to predict the future of all of the agents that we care about. And it's important to understand that inherently it's a prediction. So it cannot be deterministic. The world that this happens is a probabilistic world. So you have these different paradigms. One of the most prominent ones is the multimodal predictions, which means that you have different modalities, and then for each modality, let's say the vehicle is going straight, left or right, a lane change or something like that. For each of these modalities, you have assigned like the modal prediction, and the uncertainty maybe laterally, longitudinally, or time-wise, you have the uncertainty bounds of that prediction. So that is kind of the industry standard, mostly a multimodal prediction. In this case, you can see most of the agents have some sort of in this case, like multimodal prediction. And on the right side, you can see the uncertainty bounds of each prediction. The larger the circle, the more uncertain it is. So that is the time, I think in this case. So let's say this just 5 timestamps from t equals to 1 till t equals to 5. So you're predicting where the agent is going to be. And as the time factor increases, you are more uncertain about the future, which is a very normal concept, right? Which makes sense to us. And this is done using like the uncertainty mathematics that we have, the probabilistic understanding, the Bayes theorems. So we will probably get into more details on the exact specifics within the bootcamp, but just a high level overview of where we are. Okay. Yeah. I don't know why it's coming out here. Okay. So some of the approaches for these predictions is a model-based prediction approach, which is essentially the most mathematical way of understanding how motion works. You have physics models like a constant velocity, constant acceleration, and then you might have some rule-based models, such as you have some agents, you want to follow them. So in this case, the intelligent driver model is something which is used by the industry, where you have agents moving on the road, and we assume that they will follow the rules of the roads. And then you can use your normal your control laws, your velocity targets, and you can actually forward propagate them to compute these driver predictions. So you can have an ego prediction, you can have other agents predictions based on this. So this is almost like traffic flow information. So you assume that the traffic is going to have like some sort of flow, and you're trying to model that flow using these mathematical models. In this case, we are showing that, yeah, we are following the lead vehicle with a safe distance. And there is a very nice mathematical formulation of doing this. And then some social force models, which more are like the robots that we have for attraction and repelling from the agents and attracting to the goals. So these are some different ways of generating these model predictions for the other agents, and including yourself as well. And the key benefits are they are very like highly interpretable. You know the physics. They're very fast to compute, and you don't require a lot of training data for these kind of models. And some of the downsides are they might not correlate exactly with how real world data is. Real world is inherently messy, does not follow many rules sometimes. So yeah, that is to take into account the messiness of the world, the uncertainty. You probably need something more than this, but this is a good starting point for most of the prediction models. Yeah, as I alluded to, data-driven approaches are where like we have a lot of data already available. And this usually means that when any kind of a robot is driving through the scene, you are already logging the other agents' data of where they are, where they will be. So all of those things combined leads to a large corpus of data for which you can train your models in. And those models will then be able to predict in a lot of cases where the future lies. And as I said, most of it will be a multimodal prediction where the agent wants to go, and all of the probabilities of these multimodalities will sum up to one probability of one. So that's what you want it to be, and that helps us in the planning side as well to like know, okay, how likely is the agent going to be going straight versus taking a left or a right, or in the case of a highway merge, are they going to be cutting in front of us and we'll have to hard brake, or are they going to be merging ahead of us by speeding up, or are they going to slow down? So these are all different modalities, different homotopies, and the multimodal prediction will give us all the information that we need. And it's now up to the planner layer to decide how to deal with that multimodal information, and we will get into that as well later on. And then yeah, we some important things are that you want to condition these predictions on different things. So one important thing is map conditioning. So we want most of the agents, we know that they follow rules of the road. So it makes sense to have some sort of map aware conditioning and also other agents conditioning, not just map, so that when you're making a prediction, the more context you have about other agents, other interactions, and intentions, the better the prediction can be. And we will get to this later on. But in this world, what we're talking about is more of open loop predictions. These are just predictions for the other agents, and these do not take ego actions, which is the self-driving cars actions, into account. So what happens is this coupling of ego and the agent is not taken into account here. You are just giving an open loop prediction about the future of these agents. And this is like one of the challenges, and we will come and talk about this later on. But yeah, some of these things just having some map aware predictions can improve our prediction by like 30 to 40%. And then coming to like, how do we evaluate these predictions? There are some like interesting ways that we can do. And I think the high level takeaway is also about like thinking about these open loop and closed loop predictions, as I said. So open loop prediction will be just about taking the log data and making a prediction using a model, comparing it with the ground truth that you have. And then that model can use that as a loss function and train a neural network out of it. So that's the high level overview. And there are some metrics in this case, like ADE and FDE are very common, which is the average displacement error and the final displacement errors. So those are more of the theoretical metrics that we care about. And then the ratio of min AD, min FD, and the miss rate. These are some important parameters. But by themselves, open loop metrics, they have a role, but they do not take into account the interactive nature which I talked about. And it's the pros are it's fast to compute, and you can benchmark against different models in neural networks how your performance is. But the real world is on the right side here, which is the closed loop evaluation. The closed loop evaluation itself means that you make a prediction, then the agent or the ego makes its own plan, and you see how it unrolls in future. So this coupling happens in real world, and you want to see, like, was your prediction good for you or bad for you? So if the prediction let's say in open loop was perfect, and we went to a place where the prediction it matches all the training data, but in real world when you're driving, it does not give you the behavior you're looking for, and let's say in the worst case it leads to a collision. In that case, or open loop evaluation, or just the metrics, they are not very helpful. You then want something like a closed loop system, which is much harder to compute, because then you're running the whole planning stack in this case, but you do get a more comprehensive idea of how your system is performing. So this is where, yeah, we run the whole simulation, and then we check for things like, were we safe? Was the behavior appropriate? Did we have collisions? And we can compute other metrics like near misses and stuff like that, and even comfort. So those are some of the things. I think this is where we can take a break. Before that, like, I'll open the floor for some questions here on the prediction side. Okay.
Yeah,
Does
this is
anyone
Murali
have?
here. I got what is sensor fusion and getting different sensor value and fusing it to get a picture of the perception of the scene in front of the autonomous vehicle. That area, I got idea how it works and all. But this model driven and data driven, can you tell me, like, these models are like ML models, they are running on ECU, to get we'll feed the data, run against it, and or how that works, uh, to get some
Mhm.
mental picture of what is what.
Yeah. I
Mm.
think like the idea is that, yeah, once you have
I'm new to
your,
this. This is my first year research in this autonomous vehicle. So that's why
yeah,
I want to get some.
yeah, we will get into more details, I think, in the boot camp, but I can give you an overview of how we are, how you can think
Okay.
about this. Yeah.
Mhm.
So
Okay.
we have so we have some of these tracking already made, the predictions that the classification of the objects, and then
Mhm.
you are taking them, and you have a neural network which is like taking in that as the your input vector, and then
Mhm.
making a future prediction on the, like, the multimodality. So it will not have just one output, multiple outputs, and it will have a
Mhm.
time sequence information of those outputs. So this
Okay.
is where a standard neural network probably does not do well, because you might
Mm.
have like, there is a coupling in time. So this is where traditionally things like LSTM, which is able to think about some of these interactions over larger, like over time, like sequences,
Mhm.
is helpful,
Mhm.
or like a graph neural network. But lately, what we
Okay.
have seen is that a transformer architecture is actually the
Mhm.
best architecture for thinking about different contexts and different agents, and how they should interact with each other. It's able to encode much more complex semantic understanding of the world. So that is where
Okay.
the architecture for prediction is moving. But yeah, these all of these are run on the GPUs, so not
Mhm.
on the, like a specific CPU per se. It will be on GPUs, dedicated GPUs. which will live
Mhm.
on your SoC that you have in this case.
Mhm.
So I think like, yeah, that is where like a lot of compute is being used by these GPUs.
Okay.
Yeah. Okay.
Okay.
We'll
Thank
take
you.
a
Got it.
5-minute
Yeah.
break here
Yeah,
and
Yeah,
then
sure.
we resume.
perfect. Aditya, so we would take a break for maybe like 5 minutes. Would that be okay, or shall we take it for 10 minutes?
I think 5 minutes is good.
Okay, perfect. So yeah, we will go into break. But meanwhile, I have shared like link to our boot camps in chat section. So if you're like interested in any of those, just go and explore those boot camps so that you would get more details about that. Yeah. So we'll be back in like 5 minutes. Yeah. Thank you.
Yes. All right. See you.
Hello everyone, Mayur this side. I welcome all of you again to like second part of like this guest lecture. While we are waiting to, okay, just give me a moment. Okay, so while Aditya is joining us for like second part of this session, uh, I am here. If you have any question, oh yeah, Aditya is here. But yeah, meanwhile, if you
Yes.
are having any questions, just put them in chat section and I would answer them for you. Okay, yeah, Aditya, we could continue with like rest of the.
Yes. Sure.
Okay.
Mhm. All right. Yeah. Thank you, everyone. So let's continue. So now we have talked about the prediction side, and the next is to talk about the planning side. And the first layer that we talk about in the planning layer is about understanding the map, the lane level information of the maps, and the route information. So what you can see here is that this is different from a Google Map route. A Google Map route is not lane level. So that, I think that is the first question a lot of people have is why do we need a routing part or like a routing algorithm? Because we can use just Google Maps, but that's not how it works, because Google Maps currently does not give you lane level information. And even if it did, you would need your own specific context on what you want to do, what are the things you want to avoid, and things like that. So the high level idea is that you're breaking down the problem into like a smaller chunk of problems. It's called the hierarchical decomposition. So on a high level, we are trying to solve the problem, which is A to B planning. So from your current position to any of the destinations. So one of these, the routing algorithm has to decide what lanes to take and what are the exits to take for the whole map. So this is going to be the longest duration part of the planning stack, and everything beyond it is going to be looking more locally within the next 5 to 15, 20 seconds. And when you're thinking about this, think about not just having like one plan for the routing. So in this case, what we can see is, let's say we need to take the exit on the right. So the routing information will tell you that, yes, we need to go right, if possible, as soon as possible. But for some reason, let's say the lane is blocked and there's a lot of traffic and we cannot make that right exit. In that case, there needs to be alternative routes, and we need to have costs associated with them that can help the planner to know how urgent it is to make this exit. Because let's say there is a future, like if you continuing on this route, like straight on this route, uh, let's say you're going to hit the end of your operational domain. So in that case, the urgency of taking this right exit is much higher compared to the situation where there is another exit coming in a mile. So I think all of these factors are important for the routing side. uh, and then like the basics of a route problem is to model it as a graph search problem. So just to give you a brief overview of what graph search is, there is the fundamental of Dijkstra search, which is a uniform expansion in all the directions. So in this case, we're trying to go from the start to the goal, and we end up expanding everything uniformly outwards from the start states. And this is something which is a clever way of solving this problem, but you end up expanding all of the cells which are required to reach the goal. So it can induce latency in cases where you need to search in large state space. So those things are important to take into consideration. And a heuristic would be the thing which can guide this search from a Dijkstra into a star. And a heuristic can be anything which estimates your cost from the current state to the goal. And there are different cases. In some cases, this estimate can be more than the actual cost. And in a preferable case, this distance would be less than this cost would be less than the actual cost. So that is a condition which is required for making the search optimal. So what we have is the search will be optimal if the heuristic, which is in this case, the simplest thing is the Euclidean distance between the start and the goal. So in this particular case, we can say for sure that the Euclidean distance will be smaller than the actual distance taken by the search. So it is a admissible and consistent heuristics which are required to make the output of the A star search to be optimal. And what we mean by optimal is that is the best solution that exists for such a problem. Uh, then there are some variants of the A star. One of the most important ones or common ones is the weighted A star. What you will do is take the G value, which is the cost to go, and add the G value, which is the cost to come, and the H value, which is the cost to go, and you will inflate the cost to go, the heuristic value, by a particular amount, and this will make your search go faster. But this is of course at a trade-off in optimality. So what you will have is a bounded suboptimal search, but in most cases in practice, that is you're okay with those in cases where you need like a low latency search. So you trade a little bit of optimality for some computation. So that is like the high level overview, and we will go into more details how to work with search in the bootcamp itself, and different variants of it, because this is like the vanilla searches that we talk about. Next, I wanted to talk about, like, okay, routing is not just a search algorithm by itself. You're trying to solve an optimization problem. So what are the things you want to optimize for? So I've just taken an example where some of the things we might care about is like travel time, the distance, or the energy. You can think of it like if you're going up a road which has a higher like a gradient, so your energy consumption would be high. So you want to model all of these things within your search, within your routing, so that you are coming up with the optimal routes, which could be energy. And then there are some lanes which you prefer. You know that you want to drive in the rightmost lanes, let's say for a truck, versus some of the lanes you don't want to drive in. You can have some lane preferences, and comfort of like doing lane changes itself is important. So having too many lane changes will be uncomfortable. That can be a cost. A lane change cost itself is a cost. You don't want to have a route which has too many lane changes as well. So it's a multi-objective optimization problem. So what you're trying to solve here is not just having single traveling time. Yes, Mayur, you have a question?
Yeah, sorry to interrupt you, but could you please confirm the screen that you're sharing has like slides? Because at the moment, the thing that I'm able to set my end is like some link or some web page. So could you please confirm, or maybe someone else could
Yeah,
also click that?
yeah, I think it has gone to some docs. If I go, let me try again.
At my end, I thought maybe my screen is frozen, but yeah, I tried to rejoin this meeting. But anyway, just
Okay, now
so
it should be better. Is this better?
We are just seeing this Back to Future AI Stanford website.
Oh, okay. Maybe it's not sharing. Let me share. Okay, yeah, that's unfortunate. Let me try again. Is this fine?
yeah, now we could see it.
Okay. So did you guys see the screen?
No, we did not see any of those slides.
Oh, okay, okay.
Maybe
Yeah.
we'll please go through that. But yeah, we got the point about
Yeah.
extra
Okay,
hand.
okay. Yeah, yeah. So I mean, what I was saying first, I can just like give you 10 seconds to look at this slide. This is the lane level information that we're talking about, and the routing operates in this lane world, where you want to find the optimal routes. And what I was saying is like taking the exit versus not taking an exit. In this case, it is clearly shown that like, yeah, we want to take the exit, but then there are some other factors into account, like you might have an alternative route exit after this. So all of these things can be turned into a multi-objective optimization problem. And like this was where I was trying to talk about the search, the Dijkstra and the A-star search, and how we are thinking about expanding these two fronts. So Dijkstra is more uniform expansion, and it will end up exhaustively searching the whole graph till it finds the goal. And the A-star itself will be guided by a heuristic. And in this case, as I was saying, the Euclidean distance is that distance, which is directly just the distance between the start and the goal, and that is always going to be admissible and consistent, which is one of the requirements for making a search optimal. So just this is what I talked about, and now I was trying to show that how the routing itself is not just a single value minimization problem. It's a multi-objective optimization problem by itself. So you are trying to optimize for many different competing things. And this is very common in like any kind of control problem. And the way you do it is by assigning multiple weights to different things. And you are able to, using that, solve for this problem. And A-star can use that as the cost itself, and that will be used to find your optimal routes. But as I alluded to, you might want to consider not just having one optimal route, but having many such routes, because what you will see is, like in this case, the route wants us to take the exit, but in real world, let's say there's some agent cutting us off on the right side. So what will happen is you will not be able to take that exit. In that case, you will trigger a replanning of your route, or if you've already taken into account all the possibilities, you will not be triggering another replan of your routing, and you can just use your prior search that you did to guide you along this new route that you might have found yourself in. Yeah, coming back here, yeah, some of the approaches that we have here is one of the like common ones is, if you have a large graph, you can use like a bidirectional A-star, which is running two searches from both the fronts, the start and the goal, and you want them to meet somewhere in the middle. And this in general cuts about the timing by at least twice, because you are cutting a lot of large search space, which a single search would do. So you're trying to meet in the middle. This works well for this particular case where you want to go to a single goal and a single start position. And like some things, because these can be really large graphs spanning many thousands of miles, and individually could have millions of nodes. So you want to have some sort of ways to optimize for this. And something which is used in the industry mainly for like Google Maps kind of optimization is called a contraction hierarchy. So those things have some different nodes which are more important for a particular search, and some are which are not as important. So what you end up doing is pruning some of these lower important nodes, and that speeds up the searches. Like that's why like a Google Map search is so fast, even though it's searching over such a large network and such a large graph. It's able to do a lot of pre-computation beforehand, and then use some of these techniques for pruning, or some really good heuristics which can speed up the search dramatically. So I think that is an important factor to consider here. Another thing I want to talk about is like in the way you are formulating your world, any kind of lane change is not a deterministic lane change. So in general, how you would model that is you would just have a lane change action for your search. And in a deterministic world, when you think about a lane change, you are always able to do that lane change, and you pay a cost for it. But in reality, reality is closer to a more stochastic version, where you have a likelihood of making that lane change because of traffic and other things. So if you model it this is called an MDP, a Markov decision process world, where there is a probability assigned to each action. In that case, solving for an MDP of this nature is typically O(n) squared of time complexity, and this will not work. In general, it will not work on a vehicle. It will just be exponential or just quadratic in nature, and you will have really slow search. And we want results as soon as possible. So, and one interesting fact is that there are certain tricks that you can use to formulate this MDP problem as something simpler. And by having certain tricks, you can formulate it as almost like a Dijkstra and get the complexity down to n log n to make it more accessible in real time. And this is able to now handle some uncertainty in your lane changes. So I think those are some things which are very interesting to see. And the next thing, next topic itself, I can just maybe stop here if someone has any questions about routing in general before we move on to the behavioral planning layer. Anyone have any questions? Cool. Yeah, the behavioral planning is the next layer after the routing layer or the mission planning layer. And in this case, what we have is many agents have their own actions, and we want to see our own actions. Let's say we want to do a lane change or not. We can model them as separate behaviors. So a keep lane could be one behavior, lane change left could be one behavior, lane change right could be a behavior, and you can get more granular. You can have passing something on the left, you can have yielding behavior. So it can grow into a larger set of behaviors. So you have a pool of behaviors that you want to use. But in this case, a simple scenario, let's just say that we have three behaviors going straight, left lane change, right lane change. So you can model the planning as something like a finite state machine. This is done commonly in industry, but it has its own flaws, so it's not as common anymore. But there are some approaches which leverage like a behavior planning part to solve some problems really in a neat way. We will get to that in some detail a little later. But yeah, that's just the high level overview. So as I said, like a finite state machine itself is having different states. And in this case, you can have different states as a lane follow, lane change, preparing for lane change. This is more granular and emergency stopping action. So as you can see, you need to then define all of these interactions in your state, in your state that you have for the finite state machine. And this can get really complex. Let's say you have now 10 such states. So you would have to model each of these interactions. You would have to have rules for each of these transitions. So in reality, it will become really messy and difficult to extend and maintain, which is something you don't want for a solution to be scalable and generalizable. And another thing is that you can have these rule-based systems. You can properly tune that, okay, if the gap ahead of me is this much, and if there's a car on the left with this much space, I can make the lane change. But the real world, you will always be straddling on the boundary of many decisions, and it will not give you the behavior that you want. And the real world will have many such interactions and many such cases that you will not be able to write each of these rules down. So this is something you need to take into account, that you want to come up with generalizable and extensible solutions. And like in general, this is a good start for any kind of problem space. But then you would want to maybe move on to something different when you have a more complex system. So this works really well in simpler situations. And another thing that I alluded to before was this interactive nature. So now we can dig a little bit deeper into the interactive nature. So why is it that like we can not just think about planning for ourselves and like the agents planning for themselves, and that's okay? So it's inherently not how any kind of interaction works on road. You might want to merge but the other person also wants to maybe merge in the same lane or wants to like speed up ahead of you. So we are trying to solve this problem where your actions will be leading to a different action from the other agent. So this creates a circular dependency, and this is something trying to solve this for this in a real time system is really hard. And the theoretical concepts that you can use to solve such systems is modeling it like a game theoretic system. And in game theory, this is a whole field by itself. But the one of the key concept is like iteratively solving for some equilibrium state. So think of it like you have some starting states of different agents, and you want to find the state where all the agents can cooperate and be happy with their decision. And finding this point is called actually the Nash equilibrium point. And how you can, there's different ways to solve for it, but a common way to solve for it is using like a IBR, iterative best response, by iteratively iterating different actions and computing some cost, and then reaching the particular point where you cannot improve the total cost of the system. So it's not just you're optimizing for your own cost, it's a joint optimization problem. So this kind of situation happens a lot in real world. And trying to run these kind of solutions which are game theoretic on a system where you need to be giving up, let's say, a planning decision every 50 to 100 milliseconds is really hard. So that is something you need to take into account. And maybe you can do some simplifications, and that is done certainly in some cases. And we'll get more into those details as well. But generally, like, these kind of solutions work well in a smaller agent space. So let's say you only have 1 or 2 agents, 2 or 3 agents you care about. You can probably run a game theoretic solution which works really well. But then as you scale many agents, the curse of dimensionality will hit you, and you will not be able to find solutions which work in real life. Yeah. Any questions for this part, the state machine based and the game theoretic interaction? Yes, Ravi.
Yeah, hi. So, when you were saying there was a re-triggering incident that happens, let's say you're traveling in a lane and you have to take an exit and the exit is closed, and
Yeah.
the recomputation happens from that point, or the system predicts the lane closure and recomputes before it reaches to the exit point. I mean, which one is happening right now?
Yeah, it's all happening in real time. So the routing module has computed its own set of the optimal routes as well as maybe suboptimal routes, and the planning layer will try to have a cost bias towards that route. It will try to prefer that route because it knows that from a high level point of view, the routing wants you to go in that lane. And what will happen is when there are some other costs in your real world, let's say lane closure, collision, or just not able to making the lane change at all. So all of these costs will outweigh your routing cost, and the decision made will be to keep going straight instead of making the lane change. So this will happen in real time, and as you progress in time, you will end up in a state where there's no more feasibility of a lane change. So now the only feasible action is to keep going straight. And now the router itself will be left with only one choice of keeping going straight. And it will now have its own cost for that action.
Okay, so I mean, at the time of exit, when you have to take an exit, there is no exit and it keeps going straight. So going straight is a suboptimal solution till it computes the next optimal solution.
Yeah, so think of it as you want to have the optimal route, but that's a decoupled problem. The routing does not know anything much about the real world and the traffic flow.
Mhm.
So routing always needs to have contingencies as to, okay, the optimal route might not be followed, so what is the other routes? So there are different paradigms. In some cases, you would just compute all of these other routes in one go in a Dijkstra like fashion. So now you have information about like the all of the routes, and you would not need to recompute. But in some cases where, let's say, yes, you do not have the policy computed for that particular action of keeping going straight beyond a certain point, you would trigger some sort of recomputation.
Okay. Okay, so
Also, there is one thing that I would want to add from my end. Maybe that might give you like more clarity about this topic. So when like Aditya is talking about like planning, so it's something split into like three segments, and it's hierarchical. And the rate at which it iterates is different. There is a global planning or route planning that Aditya has been talking about, like in terms of Dijkstra or A star. Then comes behavior planning, and then comes local planning. So the thing that you mentioned, that like there gonna be like some object over there, so that mostly we handle at like local level, or like if there go like local planner. So it's a different thing. So there, it depends, but it would happen locally. So you might not need to change entire global plan, but you just have to think about like local plan. That's something he would explain like in later slides. But yeah, that's the answer.
okay. Mhm.
I
Got
hope
it.
that gives you clarity.
Yeah. Thank you.
Yes. Yeah, definitely. I think the picture will be clearer once we have gone through different modules. So like, yeah, the routing is the first layer, as Mayu talked about. And the second would be like a behavioral planning layer. So the important thing is, yes, the routing is not running at the rate on the local planner is running at. The local planner is running for, let's say, every 50 to 100 milliseconds continuously, but the routing does not need to run at that rate. It can be slower than that. And the motion planning also is also running, in some cases the motion planning and the behavior planning are in the same stack, so they are running at the same rate. But in some cases you can have a behavior planner running slightly differently to a local motion planner as well. So it's a architectural decision, which you can make based on like your constraints of your problem and the kind of problem you're trying to solve.
Um, just a small question in continue to the previous answer by you. So can you give one example for each planning, like local planning, motion planning, and global planning? Global planning is like, I understand, A to B, the optimal route, like how we get it over Google. Can you give one example for the other two plannings?
Yes, yeah, exactly. So, yeah, you already know the global route planning. So, in the case of behavioral planning layer, so in this case, you can see that there are two cars here, and let's say that we are controlling, let's say, the blue car. So there are some high level actions that you can think of as like I can either continue in my own lane, or I can make a right lane change or left lane change, right? So those are some high level actions, and that the behavioral plans, the so the behavior plans concept, or just what we are trying to achieve from it is, okay, what is the optimal behavior? So we are trying to, so you can see that if we are modeling this as a finite state machine, you can have a preferred behavior. So what will end up happening is that you are, let's say, in a lane follow state, and you can keep being in the lane follow state unless certain conditions are met. So if certain conditions are met, let's say route requires some change and there are some gaps that open up, and you can then prepare for a lane change. You might fail and then come back into lane following. And then what will happen is that, let's say you are successful in doing a lane change, you will transition to the lane change state. And from the lane change state, you then can, maybe you'll probably, once you're established in the lane change and you complete the lane change, you will go back to lane follow, because now you have established yourself in the new lane. So this is like the behavior part, where you're just thinking about your behavior into some high level behaviors, because it is easier to like understand and compute, compared to just having like not having any behaviors that you're following. Then you don't know, you're just making your problem harder by having a larger set of problems to solve for yourself. This is a way to simplify some of the problems by having like classifying your actions as certain behaviors. So this is the idea of behavior planning layer, is to, okay, what is the best high level behavior for this moment, And then the third layer, the motion planner itself, is like once some high level behavior is, it's already satisfied. Okay, we want to do a lane change. The motion planner's job is to generate trajectories which will be safe to do the lane change. So it itself is trying to follow the high level behaviors chosen by the behavior planner, and it will do so. The job for the motion planner is to create those like waypoints and trajectories which are safe, and it is doing the whole optimization problem of its own, because the high level behavior is just saying that we need to do a lane change, but not how we are going to a lane change, how fast, or where we are going to do a lane change. I hope that that makes sense.
Yes, now, yes, it's a clear picture for me now. Thank you.
Okay, yes. Yeah, so we can now, if there's no more questions, we can get started with the third part, the motion planning part. After the mission planning, routing, and then the behavior planning, then we are going to the motion planning part. So as I already started on motion planning part, yeah, we are talking about a particular behavior in some case. And I just want to clarify that in production, you can come across a system where the distinction between a behavior and a motion plan is not as strict. You can have a more continuous action space, and you can have a system which is like generating motion plan for different different types of behaviors that you want, but they are very closely linked with each other. So, but in general, this distinction is really helpful for understanding the problem space. So yeah, I want to start first with some more graph search. So one way of solving this problem is modeling it like it's called a conformal lattice. So what does the word conformal means? That you have a road which is having its own curvatures, and you want to follow those curvatures of the road. And a conformal lattice will create like a graph which is aligned with the roads itself. So in this case, yeah, you can see the road is curving in both the directions. So we are trying to curve ourselves, and we are trying to generate these nodes, the blue points here. These are the lattice states. In this case, I've chosen a simple representation of the state space, which is just x, y, and theta. So this is just the spatial representation of the problem. And in reality, you can have even a spatiotemporal state, which means that it has both like the spatial as well as the time or the velocity in it. So yeah, the idea is to generate the optimal sequence of actions uh, using some motion primitives. So in this case, you can see we have 3 different motion primitives: the green, the purple, and the orange one. And each of them has a slightly different action. So in this case, we are trying to generate some kind of action going straight versus. So this is where I was talking about that this system is not as divided into behavior planning and motion planning, because it is continuously discretizing that action space into the motion primitives via the route of motion primitives. So in this case, the green one is going straight, the purple one is going in between the lanes, and the orange one is actually making the lane change. So when you model this as a graph search problem, you can try to find the optimal sequence of these motion primitives. And the problem is complicated by the fact that we will have other agents in the scene. So you cannot just have a simple spatial representation. You need a time representation. And when you add another the 4th dimension of time explicitly, your state space will grow exponentially, and you will hit the curse of dimensionality, and that will lead you to really not finding solutions in the time that you're looking for, the 100 milliseconds that you're looking for. So in a lot of cases, you will be able to simplify your search, and you will need to do some really really good heuristics that needs to be designed. Or in most cases, what ends up happening is you end up making your search algorithm very greedy, and you give up on optimality. And having some sort of heuristic is helpful, but also having some sort of machine learned guidance is really helpful. Yeah. And then in this case, what I'm trying to also show is that is one approach, but then there are other approaches. Sorry, my cat is trying to get into the meeting. I'll let her out. Yes. So yeah, that is one of the approaches to model it as a search. This has its own pros and cons. As I said, the search will end up becoming greedy and not so much optimal. So you would rely on some other methods like heuristics or ML to guide your search, because you don't have as much time to search for a lot of your answers. And another approach that we also see very commonly is using the Frenet and optimization framework. So this is where you have, let's say, the output from your behavior, your finite state machine or your behavior planning is that, let's say, the solution that we're looking for is following the trajectory and keep laning in our current trajectory lane. So that would be the green line that we see here. That creates a reference path. And then how the Frenet coordinates work is you break down your world into some longitudinal and lateral states. In this case, it is called S and D. And you sample a bunch of these points around your references. And then there are different ways you can solve for this problem. You can either do a decoupled planning where you're solving separately for lateral planning and for longitudinal planning. So the longitudinal planning will give you speed and the lateral will give you steering. But you can also couple them into a single optimization problem and generate these different different sample points. 1 second. Yes, sorry for that. Yeah, you can generate different sample points along the path, and these will be aligned to your reference path. And then you can generate the whole trajectories using some quinting polynomials or some other form of connecting, like solving the boundary value problems. And then these terminal states, once you sample them, you can generate primitives, and then you can have a costing mechanism. The costing mechanism is where most of the behavior, the optimal behavior, is encoded. And how do we care about that? Like optimal behavior could be things like comfort, safety, rule following, and some other things that we care about, like, let's say, lane preference, routing. So all of these could be different part, similar to the multi-optimization problem we saw in routing. This could be a multi-optimization problem. And here we're trying to find, once we sample multiple such candidates in, let's say, both spatial and temporal states, we then just are able to cost them and select the best one. The really good point of this is that you do not run a search over successive states. You can parallelize pretty much all of this process. So from generation of the motion primitives to even the actual costing. And this is where like the modern GPUs can be used, and you can move a lot of your actual computation onto the GPUs as much as you can. And if not for GPUs, you can also just use your CPUs, multi-threads and multiple cores to parallelize most of these actions that you have, or most of these samples that you have, because they are independent. All of them go from your start state to some final state, and then you cost them and choose the best action. So it's kind of like an MPC where you are generating multiple candidates and you're driving the first candidate, that the optimal candidate that you found. So that is the high level overview here. Then, yeah, any questions here till now for the structured part? Okay. Yeah. Now, there are some cases where it's not just a structure, it's also the unstructured world. So in those cases, let's say we are in a parking lot and we need to park our car between two cars. and that is not following any lanes. So this is an unstructured problem. There are many such examples where it could be unstructured, doing a 3-point and multi-point token. So in those cases, following the conformal lattice or the Frenet coordinates is not required. In those cases, some of the common methods that you can use is like it can also use like a lattice search. But the most common, I think right now, or is seen as like a hybrid state A star, where you have your particular like your motion primitives defined for your agent, and then you do a search, and then the hybrid state, what the word hybrid state means is that you are trying to take the continuous actions and map them into some discrete space. So let's say that you have a 3-dimensional state space in x, y, and theta. So the action themselves will lead you to a continuous coordinate, but you will be snapping it to the nearest discrete cell. So this helps to keep down how many nodes you expand and what is your branching factor, because you are discretizing the space. And you're ensuring that any kind of action is kinematically feasible. So you go from having kinematically feasible actions and expanding the search. You can also have forward actions and reverse actions. So this will lead you to have very natural solutions to like parking problems, multi-point turns, and you will end up finding that, okay, if you're able to reach the goal and you create this graph, if there is a solution which exists in the graph, in the resolution of the graph, you will end up finding the solution. So we will go into a lot more detail on these things in the bootcamp. Yeah, but a high-level overview is that here also you use some heuristics, and the two common ones are the non-holonomic and the holonomic heuristics. So the way to think about heuristics here is to divide the space into subspace, into subproblems. So in this case, the 3-dimensional space that we have is divided into a 3-dimensional space without any obstacles, which is the non-holonomic constraints. So something like a reed-shaped path can be used, or there are other things. This totally ignores all the obstacles. Or you could do a like a holonomic one, which is considering obstacles, but is only doing obstacle avoidance and not taking into account your non-holonomic constraints, which means your curvature limits, and essentially the robot can move on the side, so it can like sidestep. So you then combine these two heuristics, which are like the subproblems, into a single heuristic by taking the max. And by doing this, you are able to get like your optimal solutions. And then there is a whole space of search, which is sampling based search, called RRT. So just a high level overview is it's called rapidly exploring random trees. It will generate some candidates and it will try to connect them and grow your tree. So this is it is by the virtue of it being non-deterministic, because it's random. Sometimes the solution will look different, but this works really well in a high dimensional space where you don't have time to search for the exhaustive search space. So that is where like having a higher dimensional state space can lead you to use something like an RRT or variants of the RRT, like RRT Connect, RRT Star. So yeah, that is just what we are discussing here. We will go into more details in the bootcamp. We will actually solve some of these problems practically. Yeah, in lieu of the time that we have here, I just want to speed up a little bit. So collision checking is a major part of the problem space that we have. On a high level, you can do collision checking between different, let's say, obstacles. So this could be pairwise, or you could compute like a pre-computed obstacle world. So that could be an occupancy grid. And then your pre-computed motion primitives can be used to do collision checking using some sort of distance field and things like that. So there are different methods of doing these kind of collision checking. Then there is also some lazy evaluation techniques, which allow you to speed up the search by not doing exhaustive search, by only doing some selective searching, and then collision checking only on certain parts of the graph that you care about. And those are all viable techniques to speed up your search. And as I already touched on, you can parallelize some things. And in general, search is hard to parallelize, but some parts of the search can be. And yeah, that is kind of the high level overview here. And next I want to talk about is, I think this is probably the last topic, is like how there are some real world challenges that you have here. And what are those challenges? How do we tackle them? Where do we use machine learning in planning? Stuff like that. So before we get into that, any questions for the last part that we did here for unstructured planning?
Aditya, there are some questions in like chat section, but maybe we could handle them at the end of the session in Q&A session.
Yeah.
I mean,
Sounds
you
good.
just,
Yeah. Yeah. So yeah, as I alluded to a little bit before, we have some real-time constraints running on real-world SOCs that you have. So what you want to do is come to a decision fast. And by fast, I mean like 100 milliseconds end to end from the perception to the control is like the ideal timeline. In some cases, that will not happen. You might end up making it like 200 milliseconds, but what you don't want it to be like the end-to-end latency to be like a second or half a second, because then you are acting on stale data and you will make suboptimal decisions, and those will not be good. So this is where like this is kind of like a sketch of like the times that you might see, like 10 milliseconds for perception, then prediction 30 milliseconds, motion planning might have 40 milliseconds or 50 milliseconds, and control might take 10 milliseconds. So this is a very tight timeline for us, like something to get a solution on either using CPUs or GPUs. So what you want to do is optimize each and everything that you can. And as I alluded to before, sequential things can be parallelized using CPUs on multiple threads and cores. But the massive parallelization happens using GPUs. And think of it like if you have some sort of mathematical data, which can be computation, which can be done using matrices, you can then do a lot of parallelization using GPUs. So this is not just limited to neural networks. You can actually parallelize a lot of the motion planning part on GPU using CUDA kernels, and like these will help you to speed up your processing times. And then some other things are like we already touched on is the hierarchical planning part, which has like, let's say, a different time that you're running at for a global or for a local planner. So you can divide your problem such that you are having more time for a particular part and like maybe stricter time for the local planning. And some other things is you might want to be looking at suboptimal solutions, and that's fine, and maybe stopping at your iterations only for after some max iterations, instead of running searches exhaustively or whatever optimizations you have exhaustively, and doing lazy evaluation that we talked about. Yeah. And then some memory level things which are important is like you want to pre-allocate most of the memory, and most of these things are running on C++ or Rust, which are the low-level system languages which run the fastest you can run on like a hardware. So C, C++, and Rust are in that category, but in industry mostly uses C++. I've worked with Rust as well in this. And you want to pre-allocate all the memory as much as you can. You don't want to do dynamic memory allocation, that is slow. Input outputs as well are slow. And then like fixed size buffers is one thing. Then the other important thing is having lock-free data structures. Yeah, otherwise you will have a lot of deadlocks between and contention between different threads looking at the same data. So those are some of the things. Then from the C++ and Python side, I talked about using like a torch script modules. So you can have some PyTorch modules that you write, and then you can load them in C++. And there are certain things, goes for like ML part as well. You can use TensorRT is becoming the industry standard now, which allows you to run these models, these torch script models on like the GPUs much faster. And it does like some clever optimization of of how it builds these ahead, like there's a ahead of schedule AOS and some other optimizations. It clubs together different operations like the addition, multiplication parts into like single CUDA kernels. So these are some of the things that people do to speed up their GPU part of their code base. Then I wanted to touch on a little bit on the open loop and closed loop, which we previously also talked about. Is that open loop planning means that you are driving everything that you see, like you are driving from your current state, but you're not following that plan. So this could be something like a shadow mode. And this is more akin to evaluating something, evaluating your motion planning pipeline in an open loop system, versus in real world, you will have a closed loop problem where whatever you plan, you will drive, and that will lead to a different world unfolding in front of you. So these two things can be thought about as two different things, and open loop planning can be evaluated, but it is fast and efficient, but it's not reactive to other agents. And then the closed loop planning is more realistic and robust, but it is computationally slow. So there's a fine balance to strike here. And some of the evaluation gap that we see is that open loop evaluation is fast. So we do have a lot of data sets for this. But the closed loop evaluation, because it needs to run the whole simulation environment, it is slow. And there is actually not a very strong correlation between something which is doing really well on an open loop data set versus a closed loop data set. So that is something we need to take into account. And the other thing is, we were talking about training on expert states in open loop data, but these become problematic when you go out of the distribution or where you don't have a lot of training data in this case. So you need some like other methods to correct for this, and we will talk about that as well a little bit in more detail in the bootcamp. Yeah, so dealing with the uncertainty in planning is a very, very important part. And what is uncertainty? Usually there is two types of uncertainties. There is aleatoric uncertainty and epistemic uncertainty, which just means aleatoric means that like your action itself is random. You as a driver might not know what you're trying to do in a second or two. So there's some randomness in the inherent nature. And the other part is the model uncertainty. So the model itself is not sure about its prediction. So that is the model uncertainty. And this goes for modeling any kind of interaction or agent or prediction. So just I've shown an example of how would you deal with, let's say there are three different actions in this case with different probabilities. So you can yield, you can accelerate, and you don't know what is the other one. So how do you deal with many of these actions when you're doing planning? So these are three cases that I'm showing here. One is the worst case. So you assume that all three are equally likely to happen, and you try to plan for all of these actions, which in real world will make you very, very conservative and cautious. It's because you're planning for something which is very unlikely to happen. So this is where you see some of these AV systems, self-driving cars become like stuck on a unprotected left turn for a long time. So yeah, a happy middle ground is, or like the other side, let's say first, is the expected part, which is you only consider the most likely path, but then that would make you very aggressive and also unsafe in some cases. A good middle ground is using like a variable coefficient on this particular chance constraint. So what you're trying to say is you only consider probability of collision above certain value, and you will typically have like very good guarantees on safety for that. So let's say like any kind of collision which is like more than, let's say, 10% or 5%, we will consider that. So those are, or any kind of prediction with a certain probability, we will consider that. So these are some of the things, and I want to like say that like MPDM is something we will discuss a lot more in the bootcamp, but this is a very nice way to deal with uncertainty that we have in our planner, in our system, and we will actually implement parts of this in one of the boot camps hands-on. And something that we talked about previously is joint prediction and planning. So just to like close the loop here on joint prediction and planning, we want to think about the interactive nature, and the current architecture which the state of the art is going towards is having a shared encoder transformer architecture and having a prediction head and a planning head. So these will feed into both the prediction and the planning, and they're both aware of each other. So this is where these interactions become much more co-joined, and you are able to see some really good wins in your behavior. And lastly, I would like to say that like ML in the motion planning part is also something which has different forms. So you see the most common one is imitation learning. You have a lot of expert behavior data, and you want to create a mimicking system of the expert. So that is imitation learning, and that has its own pros and cons. One of the cons is that you will run into something called a covariate shift, which will mean that you have seen you're going out of distribution, and there is a solution for it called data set aggregation. So we will maybe talk about these things in more detail. Then another thing is inverse reinforcement learning. This is where you have the data that you want to, the human expert data, but you're trying to learn the cost weights and the costs itself. So this is where you are inversing kind of the reinforcement learning problem and learning these costs themselves of your own cost. So rather than manually hand tuning your costs, you can use an inverse reinforcement learning method to get the weights from your expert demonstration data. And the last is reinforcement learning, which is, I think, like the most underutilized part, and which is probably going to have the most wins in the long term. We're already seeing some really cool impact and papers on this. So inherently, it's hard to design a reinforcement learning system for autonomous driving, but it is shown that you can design something and then it can have really good benefits for a RL kind of system. And you can even have costs in your cost terms as like a RL learned cost. So yeah, that is kind of like the high level overview. We'll probably go into more detail in the bootcamp for that. Yeah. Now coming into like, okay, what are we trying to do in the bootcamp? I think that's before that, like I would say that any questions on the ML planning side or joint prediction or uncertainty? Okay, maybe we can do the questions later. Yeah. So Mayur, do you want to take over this part?
Maybe you could like get in details, but before we go towards like final Q&A session, I would just want to convey some details. That in chat section, I have provided like link to the courses. And second thing, I also shared like feedback form that you could fill in, and you could give your feedback regarding this session and what all things that you would want to see in a bootcamp. Also, if you are interested, just let us know so that we would reach out to you with all the necessary details so that you could enroll in the session and like learn more about this domain of motion prediction and planning along with Aditya and me going forward. Yeah, so that thing is available, or that information is available in chat section. But Aditya, you could like tell more about this bootcamp, and if there is something that I would also join in.
Yeah, definitely. I think like what we discussed today and went over today was the high level overview of most of the things we will cover, but that is also the high level overview of in general what exists in the motion planning and prediction space. So we will go deeper because we will divide this into 3 sessions of 90 minutes. We will go deeper, and I think the more important thing will be some hands-on experience. including like the first session will have some prediction implementation, which Mayur, or I think we might have some expert in that area as well. And in the planning side, we will also do a lot more hands-on using Colab, using some of these lattice search or some routing algorithms that we have. We will have more hands-on experience for the classical planning algorithms part. And the third part is more the uncertainty and the ML side that we have. That's the third session. And we will also implement some MPDM kind of planner. And then, yeah, you will learn whatever you learned today, looked at today in more detail, in more depth, and we'll have more time to discuss and more deeper questions we can do. And I think the doing things by hand will be a really good lesson for most people who are really interested in this field and want to grow in this field. Yeah, that's what I wanted to say. Do you want to add anything, Mayur?
Yeah, so you have like most of the things, but regarding like projects, I just wanted to convey like means right now we are running like this control bootcamp. So maybe if possible, we would try to share some material from that bootcamp in motion prediction or motion planning bootcamp as well, because as Aditya mentioned, you would also need to have like some hands-on experience on C++. So if there are some lectures or like project that I could share from that bootcamp over here, then definitely I would do that. And all these three projects would be hands-on, and this is something would make like really good fit for your portfolio if you want to go to like recruiters and show, okay, these are the skills that you have, then yeah, it would definitely help. So if you are interested, just enroll, and then we would let you know about like the start date for this bootcamp. So that's all. Maybe Aditya, now what we could do is like we could cover questions that are available in chat section, or maybe we would open up for like one session in general.
Yeah, sounds good. Yeah. Okay, I will go from the beginning. So I think, yeah, we have some videos and pictures. Yeah, my LinkedIn profile, I think, Mayur, can you share that with them?
Yeah, sure.
I will answer the rest of the questions if you can in that time.
Yeah. I'll pull it.
Yes. Okay, so yeah, there was a question about Cruise having 1.5 robot workers, Zeus having 3. Yeah, I mean, at that time, yeah, probably that was the figure, but these numbers are always like the idea that you're working on that problem is to make these number go higher and higher. So that is like as a job as an engineer myself, I will be like most of the work I'll be doing is in improving the reliability of the system, so that we would not need to use a lot of human intervention. And most of the things that you can automate and do without human intervention, you will try to do that. So that's what my take on that is. Yeah, so Sai is asking about perception to planner latency, how to address it. Yeah, there is an inherent latency, which is, as I said, you can have some perception data and prediction data in between. Both of these will take, let's say, anything anywhere from 10 to 30, 40 milliseconds. So whatever the planner is seeing is old. What you can do is like try to speed up your planner as much as you can. So that means utilizing as many of your cores and GPU as you can, and making sure that you are planning with as much fresh information as possible. So I hope that answers your question. Do you have any other follow-up questions, Sai, if you're here still?
Maybe he's not here, but we could continue like question.
Okay. Yeah, how does planning get integrated into mapping? Yeah, so that is an important question. Like mapping is the like you do there's many ways. I would classify mapping into two parts. There is the offline mapping, which is done as a priori. That means all of the cars that are driving on the road in the initial phase, they will just be mapping the lanes and the other information about your roads, stop sign, and the curb and everything. So that is the offline mapping. Now there is another layer called the online mapping, which is becoming more and more prevalent because the real world keeps on changing. So mostly the online mapper would be an ML module now, which can adjust your map, give you different lanes. This would react to, like, let's say cones, road closures, or a new way that was made temporarily, or some barriers that were placed there. So you are using the maps as a priori information, but that does not mean you can trust the maps 100%. So what you'll need to make your system is robust by having some sort of online mapping mechanism in some cases, if you are doing the modular approach. And mapping is also used in different places, like routing uses maps to generate the route level information. Then the planner uses a lot of maps information to get things like the semantic understanding of what lane is where, and where are the stop signs, where is the traffic light. So those things are helpful for a map, for the planner to get information from the map. So those things really improve the quality of your solutions. So in my opinion, like doing mapping is really important if you want to have high reliability solution. But mapping itself does not mean that you are relying on old maps, or some mapping has become really efficient in the last few years. It's not as expensive anymore, and you anyways are doing some online mapping because of the world is changing. So yeah, that's my opinion on that. Some sort of lag or glitch in the route of maps, what would be the course of action? Yeah, I'm not very clear on what you mean there, but like, yeah, if there is something, let's say the router is not working, then you would design your system to have some sort of safe behavior, which could mean that if your higher level component, this goes for even perception. So if you cannot trust perception or routing, you might have to come to a safe stop. What that means is you have either a choice of using the last the last route that was available, and keep on driving on that, because the routing world does not change a lot. So if you are able to drive on the last available routes, that is great. But if you can't, then you might have to come to a safe stop or do a pullover. So you have to design your whole system to reach this state in case of some higher level failures from perception, routing, or otherwise. Yeah. A few words about behavior trees and planning. Yeah, the behavior trees. This is the other part of the finite state machine. Behavior trees model actions like trees. So you can have some like parent node and some child actions. So what you will do is you will go and only transition from yourself to your child's. So this is actually an improvement in some ways over the finite state machine, which might have more interactions. So behavior tree, you can have like limited set of interactions, and it is more extensible by design. The data structure used for behavior trees makes the system more extensible. So I would say that it's in some ways as an improvement, but still it's a design choice. In some cases, it's hard to design a behavior tree because there might be more complex interactions. So in general, like the complexity of your problem will decide whether you're going with a behavior tree, finite state machine, or like a fully stateless kind of motion planning algorithm. Nice slides. What software you used to make them? Yeah, so I got most of my material myself, but I did use, so for some of the slides, I used Gemini for just making pictures. For some of the other things, I actually used Claude to generate SVGs, because I think Claude does that really well. So that's what I used. And okay. I understand that the bootcamp should give overall understanding of pipeline industry method. What about any cutting edge research if one wants to dive deeper? Do you plan on giving insights? Yeah, good question. So we want the bootcamp to not just be about like something which is also available outside, which would be just a course on like, okay, how do you do A-star search or this and that, because those exist already out there. We will give you more practical insight, and also like have links to the current state of the art, and also discuss, as I said, like I will go in depth over a few things that we can cover. One of those things is using RL in motion planning. The other was MPDM, which I really want to discuss. So we will discuss more of these methods, which are kind of the state of the art in some way, if that helps you. Do you plan, okay, as well as maybe enable groups to continue work on them? I think that's something Mayur can answer.
What's the question again?
Yeah, I think Vari V is asking about like, is the first of all, I answered the part where like, okay, are we doing anything more than just understanding and industry methods with deeper research? But the second question he's asking is enabling groups to continue work on them. So creation of some sort of groups to work on some research problem. I think Mayur has more experience in those things.
Yeah, so thing is that like means in our case we've been like running one WhatsApp group, so it's there. So we have like more than like 900 people as part of that group. And funny thing is like earlier I was like running such projects in different groups. But thing is that like means we, in order to run such projects, I need like volunteer who need to come forward and they need to take responsibility for those projects, because eventually it's just me or
Yeah.
like whoever will join. So I need to take lead and I need to tell people, okay, this is what we need to do and this is what progress that we have achieved up now. So
Yes.
definitely we could try groups, but for that purpose we need to have like more volunteers.
Mm.
But if not, we could just continue with like these boot camps, and we would try to give like more projects to you so that it would become much easier for you. And in this situation, that responsibility with us, so that we could help you with like all the material that you need, and would make sure that you build that project entire in
Mhm.
entirety. So yeah.
Okay. Yeah. Yeah, I think that makes sense. Yeah, we need some leadership. So if you're interested in taking leadership for a particular group that you think is your expertise area, or you want expertise in, yeah, you can contact Mayur for like taking leadership and also guiding other people, because this is, yeah, uh, that's one of the ways you can become good at something.
Yeah, sure.
Okay, can you comment about the Chinese startups and ecosystem from your early side? Is it up to Waymo level? They're also planning global operations. Yeah, I cannot comment a lot, but from what I've seen, there's no, I don't doubt that they are good. But the only grain of salt is how much can you trust the data coming out of there. So like whatever they're saying, I always personally take them with a pinch of salt, the miles and everything and the numbers. But yeah, there's no doubt that the technology is already maybe catching up. It's just now showing if you are sustainable, you're financially profitable, and also safe enough over like like billions of miles. How
uh,
many? Yeah, how many GPUs were used? Car is in motion in general. Yeah, I mean, there's like different architectures, but yeah, in general, there's multiple GPUs, multiple flops of GPU compute power. I think it's more about the compute power than the single GPU size or like number of GPUs, because you need to be running models which are now going into some billions of parameters. So you need a decent compute size, and also you like now, like ML is being used, or GPUs are being used across the stack and not just in prediction anymore and perception anymore. So yeah, the
so maybe
cost
like
I
I would
can,
add like
yeah,
some, yeah,
yeah, go
maybe
ahead.
not on cost side, but on like compute part, maybe I could comment a little bit. But yeah, you just need to look more into resources for that. But thing is that like means what I have read is like means in order to run this stack end to end, some you need like somewhere between 200 to 500 tops. That's like your operation per second. So you this is
Mm,
how you would be like measuring your compute power. So
yeah.
if you want to run perception, prediction, planning, and control, this is this much compute is something you would need. And just to give you like
Mhm.
one highlight, like NVIDIA Orin that you get, it would support like 64 tops or something. So on the basis of that, you could decide like how many modules that you would need or associates that you would need for your operation. Yeah,
Mhm.
regarding cost, you just need to do that math for yourself, because I'm not aware about the price for NVIDIA Orin. But yeah.
Yeah, yeah. I think like a chat GPT will answer that question better than us.
Yeah.
Okay, what is the level of quantization generally applied? I'm assuming you're talking about the models. Yeah, I've seen like going down from 32 to 16 bits and even INT8 in some cases. So that's what I've seen. I'm not sure. I'm not an expert in that area. Mayu, do you know anything about that?
I haven't seen like people means people are doing it obviously, but means in some cases I've also seen where people are trying to say on compute part they are like going as down as like 8 or something like that, 8 bit.
Yeah.
Or in some cases for LLMs they are also going 4 bit, and
Mm.
it's also like noticed like in some cases they are performing well, but
Yeah.
yeah, means you need to compromise somewhere if you are like doing that quantization. So but that's the thing.
Yeah. Yes. That was the last question in the chat. Anyone else outside of the chat questions?
Guys, feel free to unmute yourself and ask questions so that we could answer it. Otherwise,
Yeah, you can ask me like anything outside of this tech talk as well in general. Like if you want to be a part of the industry, and like if you have any other questions as well regarding how do you get better at something so that you're like overall a better candidate for this thing.
okay. Maybe like we are not getting any. Okay. Does someone want to ask question? Please feel free and go ahead and ask.
Okay.
Okay.
Yeah.
I guess we are good then. Okay. So since we are like well over time, so okay, can you share your email? Maybe at the Raghu is asking you. Okay, nice.
Mhm. Mhm. Okay.
There are a
Yeah, I
couple of
can.
questions that are coming in.
You can contact me on LinkedIn, Raghu. I will accept your like invitation, and I'll answer the next question. Get into autonomous industry with no experience. I see job posting in US. Yeah, it's with like I would say like you need to get some experience in whatever capacity you can, and that could even be working for some smaller company startup. Doesn't have to be autonomous driving. Any robotics, I would say there's a lot of overlap. So yeah, I'm my next venture in my career is going to be in agricultural robotics, which is very different from other forms, but there's a lot of overlap. So just get started on something small, open source, like trying to understand and contribute to open source, like AutoWare or Apollo Go. Those could be good. And in general, like yeah, you need to, for getting a job, you need to have some sort of experience to show. And also most of these jobs will also want you to be a decent software engineer, so you need to practice your data structures and algorithms, lead code, and like those are also hand in hand, because as much as you are a motion planning engineer, in most cases you are more of a software engineer as well. So I would say start working on like getting a hand dirty writing software. Give a lot more interviews, whatever interview opportunities you're getting in your field, or maybe in some other computer science field, because interviews for data structure and algorithms would be common. So getting experience is helpful. Yes.
Okay, so I guess we are like done with all the questions, and we are like all well over time. So I guess it's time to conclude this session. So first of all, I would want to shout out to like Aditya for you for taking time out, preparing such wonderful presentation and delivering it again fabulously. So thanks to you for this. Means for me also, like there are a lot of things that I got to learn. So thanks to you for putting it together. And I also want to thank all the participants for joining this session. And if you are like interested about motion prediction, motion planning, and if you want to join this bootcamp, then feel free to reach out to either Aditya or me on LinkedIn. And I have already shared like our LinkedIn profile in chat. So you could go and check it over there, or you could just like normally connect with us either on email or like maybe or not, sir, because we are also connected over there. And then I would provide like more details about the bootcamp that we are offering. Yeah, with this, I want to thank all of you once again, finally. And with this, I would want to conclude this session. Thank you, everyone.
Yeah, thank you, Mayor.